This week, we'll start working towards making maps of thermodynamic parameters like the LCL and LFC from sounding data. So this involves a lot of data processing and data parsing, some computation, and then eventually gridding and map making. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week we're going to start working on making some maps of derived thermodynamic parameters like the LCL, LFC, and really anything else that you could imagine. In this case, we're going to use soundings because it's a great opportunity to showcase the Iowa State Upper Air Archive and how we get to that using Siphon. Then we're going to use some NOAA.gov products to get the locations of those stations. Then we're going to compute the LCL, grid, and plot it. But we won't get to all of that this week. So to start off with, we've of course got imports. So from datetime, I'm going to import the datetime object. From metpy.units, going to import our units registry. From the Siphon simple web service module, again, use tab completion there. That Iowa State, we're going to import the Iowa State upper air object. And we're going to import pandas as PD. That ought to be enough to get us started. So first, I'm going to create a date, just so I don't have this hard-coded anywhere else in my code. So we're going to create an instance of datetime, 2021, 6/13/0Z. Using the Iowa State upper air object, we're going to use the request all data. So request data just gives you data from a specific station. Request all data says I want everything for this date time. So that will take just a second there to go out and grab. And when we do, if we look at the head of that data frame, and then we can look at the tail as well, we can see it's just one big data frame with all the stations smushed together. Well, that's fine, but we also notice that unlike when we get data from Wyoming, we don't have the Latin law and elevation of the station. So we're going to have to do something about that. Now, searching around, I was actually able to find at ruc.noaa.gov/rayob/stat2000.txt this big text file that's got a bunch of identifiers and Latin lawns and some other columns here that I wasn't able to find a great description of what they all are. And it's certainly better than nothing or having to go look these all up. Or there are some tables in MetPy of surface stations, but they don't always line up with where the radiosonde is. So we're going to try this and see if it works. That's the great thing about Python, is it lets us try things very quickly and easily. So I'm going to create a variable called stations. And based on the station column in df, I'm going to use the unique filter. And there's all of the stations that are in this particular day of data. If we look at the length of it, it's 112 stations to be exact. So now let's read in the locations from that text file from NOAA and see if we can line them up. Now, one thing that I did notice in here is many of these stations have multiple row entries. Some of them change very slightly the Latin lawns, but most of them stay the same. So what we're going to do is just use the first entry. I'm going to grab that URL. We're going to call it df locations. I'm going to use pandas read CSV. And the very cool thing is we can just pass it the URL, and it's going to recognize that that is a URL go out and grab that for us. We don't have to have a local copy. We're going to set lim whitespace to be true. And if you noticed the first row here, we need to skip. So skip rows equal 1. Use calls. I don't really care about all those other columns. In fact, I'm not sure what they all are. So we're just going to use column 0, 3, and 4, which correspond to the names station, lat, and lawn. So now we'll look at df locations.head, and that looks like what we want. And you can see here, for example, the very small changes in lawn and lat for the same station identifier. So now what we need to do is figure out which stations do we have locations for. We have 112 stations. Do we know where they all are? I'm going to create a list called stations with location. It's an empty list. Now we could write this in a little bit more complex list comprehension, but I think it would be a little too much in one comprehension, honestly. So we're going to go ahead and write the whole for loop out. For SN stations, the station ID is going to be, we're going to drop that first character you see in the locations text file. It's just the 3-letter identifier, so not KOUN, just OUN, for example. If the station ID is in df locations, the station data series dot values, then stations with location dot append, and we'll just append S, actually, the full 4-letter identifier. Else, we're going to print a message to ourselves here that says no location for station and the station ID. When we do that, we see there's only one location that we can't match up. It's SYA. So if we look at the len of stations with location, it should be 111, and it is. So now we know that we can match up the stations with their lat lawns that we're going to need to do a map later on. So let's go ahead and do the calculation. We're going to import metpy.calc as mpcalc. Import numpy as np. It's always handy to have that available. I'm going to create separate lists. We could do a lot of data structures for this, but the point of this video is not to focus on data structures as much as it is to focus on how we could attack this problem, which is a little bit tricky to deal with. So I'm going to create a list for each of these things. Stations, lats, lawns, LCL pressures, LCL temperatures. Now we need a loop for S in, and now it's going to be stations with location. We're only going to use compute cycles on the stations we know we can map. I'm going to get the data for that station, which is in the data frame. We're going to index where the station data series is equal to S. The index of the surface data point, remember when we calculate LCL, we need surface, temperature, pressure, and dew point. And I don't want to know, or I don't want to depend on, is the surface point always the first or always the last? Not what I want to do. So we're going to find in the pressure data series of the data for just that individual station, what is the index of the maximum value, or the surface pressure. So the surface temperature is going to be data, the temperature field, index, and since we're going to be using MetPy's calculations, we need to attach units, which are degrees C. I'm going to copy and paste that twice here. Surface dew point is the dew point data series, also in degrees C. And surface pressure is the pressure data series, and it is in the unit hectopascal. Now we're going to do our calculation. Now if there's not an LCL that's going to be found, we're going to not converge and we'll get a runtime error. And I want to catch that gracefully and keep going. We don't care if we can't get the LCL for a particular station. We'll let ourselves know, but we don't want to just generically catch any error. So we're going to use a try except block. The LCL pressure, the LCL temperature are what get returned by mpcalc.lcl. It takes the surface pressure, the surface temperature, and the surface dew point. The station ID, remember, we cut that first character off. We're going to get the lat and lon, and we'll throw away the 3-letter station identifier, hence the underscore. We don't really care about it. From DF locations, where DF locations, the station data series, is equal to the station ID that we just found. We're going to get dot values and the 0th index. So if there's more than one, we just want the first in terms of lat and lon. So stations.append s, lats.append lat, lons.append lon, LCL pressures.append LCL press, LCL temperatures.append LCL temp. And we're going to put .m on those because we don't want to deal with units when we're trying to plot. That just takes the magnitude. Now we're going to use an except block, and we want to catch the runtime error only. And we're going to print failure for station S. And we see that we've got 4 stations that we failed, but that's okay. And if we look at LCL pressures, now we have a list of all the LCL pressures. So we've now managed to get data from Iowa State that could be very near real time. We've done a calculation on all of that data after parsing each individual sounding out. We've got a text file that had locations, and we've parsed that out. And now we've done our calculation. We're ready to start mapping and then gridding. So we'll continue this next week. I hope that you found this useful, and I'll see you on next week's MetPy Monday.